Hello and Assalamu alaikum. Okay, so today we'll be presenting the topic Six Sigma and its applications to a case study. I'm sure that you are all aware of what Six Sigma is. After all, Sir has done an excellent job at teaching us. But for the sake of consistency, we'll briefly build up the motivation for Six Sigma, going over its history and what it is. Now, if we take a look at the idea of quality, which is central to our presentation, then we'll observe that for most of history, it has been related with the idea of craftsmanship. In the old days, if you wanted a quality product or tool, you'd look out for the best blacksmith or perhaps the best carpenter. So quality was associated with an individual's ability to craft. Similarly, quality was also rare and came at a premium price because not everyone was able to offer the same consistency in skill. For these very reasons, mass production was also difficult and expensive. And neither was quality a competitive priority for the consumer or the business. However, right around the 1780s, this began to change. The Industrial Revolution saw its inception and the manufacture of products took off, as can be seen by this yellow line trend on the diagram. Machines began dominating production, replacing the craftsmanship of individuals. Suddenly, in this new setting of technology and capital, mass production was possible and even cheaper in certain circumstances. Naturally, the number of competitors also saw a rapid increase. So this increase in production and competitors made quality and quantity become essential parts of the business-consumer relationship. To demonstrate this change in relationship, let's look at an example. 10 years from now, PTCL dominated the Pakistani ISP market. The internet speed was bad, it wouldn't work correctly at times, and the general quality of service was bad. But people were still forced to deal with it because they didn't really have an option because there weren't any competitors as such. However, in the last few years, we've seen several new ISP competitors rise, such as Storm Fiber or Zong 4G, Fiberlink. And consequently, what has also been observed is that PTCL has improved its quality of services and the packages it offers in recent years to match the competition. And I can testify to that as a PTCL user. So we see how quality control becomes essential in competitive environments. And so a similar change was also observed after the Industrial Revolution. And as technology grew and competition grew further over the years, then at the start of the 20th century, there was a need for even stricter quality control. And we see the birth of statistical quality control in the 1920s by Walter Stewart, which utilized control charts to gauge the quality of processes. Then after the Second World War, when the Japanese economy and industry was destroyed, during its rebirth, tools such as total quality control and total quality management emerged. And finally, at the curb of the 20th century, the Six Sigma approach was introduced by the Motorola Corporation in Japan. So what is Six Sigma? Essentially, Six Sigma is a philosophy adopted by businesses for improving the quality of their processes. Being a philosophy is what differentiates it from the old quality management tool methods such as TQM or TQC, which only existed in the capacity of tools. Six Sigma can be adopted or viewed at three levels of abstraction as identified by us: as a statistical measure of minimizing the defects in a company's processes by 99.997%, or as a process improvement tool using approaches such as DIMAC, which we will explore further in a while, or thirdly as an organizational structure which involves trained Six Sigma professionals and teams who take up management positions and overlook the processes of the company from a Six Sigma point of view. So if we come to define Six Sigma, there isn't really any scientific definition for it, but we found this elegant description in a paper and we think it's the closest to it. So the paper defines it as an organized parallel mesostructure to reduce variation in organizational processes by using improvement specialist, a structured method, and performance metrics with the aim of achieving strategic objectives. Now here the parallel mesostructure and the improvement specialists actually are referring to the trained teams and individuals that are specially trained from a Six Sigma point of view and are kept at management positions so that they can overlook all the processes. And the structured method actually refers to the DMAIC cycles, which we will be discussing shortly. So now Binish will take over and will shed light on these approaches and as well as our case study.
Okay, so continuing with the methodologies of Six Sigma, DMAIC and DMADV. DMAIC is to improve the existing project, and DMADV is to design an entirely new process. DMADV is carried out when we know that the existing process could not be improved to the extent that it can fulfill the requirements of the improvement or like the target that we have set. The first three phases of both of them are common, which are the define, measure, and analyze phase, while the fourth and fifth phase are different. For improving, we just improve the process according to our analysis, and then we see and then we control those improvements. While in the design phase, while in DMADV, we design a new process according to the specifications, and then we verify if those specifications have been met. Sometimes while executing DMAIC, we have to shift in the middle to DMADV when we realize at the analysis or sometimes even at the improve phase that this process is not capable of the improvement that we want to incorporate in that. Moving on to the case study, we have PSG Industrial Institute from Coimbatore, India in our consideration, which is a small scale system which manufactures pumps, and submersible pumps is one of the products of this company. And the Six Sigma was implemented, the DMAIC version of Six Sigma was implemented in the production line of submersible pumps. In the first phase, we define the problem. There is a component which is a machined unit of stage casing which is used to assemble the submersible pump. It was noted that these stage casings a lot of these were having a high rate of defects and thus were rejected at the time of assembly. And on the right we can see a picture of these stage casings and the casting of this stage casing. And we defined that the problem was that these stage casings have a high rate of defect and many of these were being rejected at assembly, and thus we define the goal that we need to reduce these defects, and this in turn will reduce the rate of rejection. So we define this with a CPOC chart, which is a tool of the define phase and which gives the supplier input, process, output, and the customer to which we are supplying the finished product. So it was noted that the solid stage casing, of which the final molded machine stage casing was to be made, was supplied by the PSG foundry, and the final stage casing, which was after the turning and boring of the diameters and the whole molding, was delivered to the assembly of the PSG pumps. And the goal or the conclusion of the define phase would be the project charter, which defined the problem, the goal, and the constraints. The problem was high number of defects in the casing, and the goal was to reduce these defects by using DMAIC, while keeping in mind that manufacturing cost must not increase by too much. So we move on to the second phase, measure. Measure essentially measures the current process, and let's say what do we get if we measure or gauge a current process? We currently get a parameter which tells us how much more we can improve. Like let's say in the example, we knew that we had staged casings which had a high rate of defects. Now what exactly is that high rate in the quantitative analysis is what we get in measure. Now this measure thing is used as a set point so that we know what is the target value that we want to reach, right? And we'll know after this example more. In this example, in this particular case study, we use 750 samples of staged casings under observation, and 31 out of which were found to be defected, and we calculated the defects per unit ratio by dividing the defected units upon the total units, and then this ratio was further divided by 5 because, as we'll see on the next slide, there are 5 categories of defects. That means each unit has 5 opportunities to be defected. So the defect per opportunity was the defect per units divided by 5, and this defect per opportunity led to about 8,267 defects per million opportunities, which is a lot, and which was mapped onto a current sigma level of 3.9, which indicated that there was a large space for improvement. So this is the result of the measure phase, and this tells us how much we want to improve. Then we set a target value, as mentioned here, that we set a target value for the measured parameters, and we can, let's say we want to reach a sigma level of 5.5, and then this is also a set point used, like let's say after the implementation of DMAIC, we can look back, like we can calculate the new sigma level and look back to see the improvement on the sigma level and the actual effect of the DMIC. Moving on, we have these defects which I was talking about in the last slide, and we can see that there are 5 different types of defects, namely the casting defects, which is a defect in the raw material, ovality, oversize of bore, face out, and others. These 4 are the defects caused during the process, and we can see that there are a total of 31 defects, and we can see the cumulative percentages in the last column. Moving on, we use this data for the Pareto analysis, and as we can see that casting defects and ovality are the main causes, or are the vital few, which cause almost 81% of the defects. So the company or the DMAIC team concluded the measure phase with the fact that casting defects is because defect in the raw material. It was communicated to the production company of the casting defects, and they were expected to be lower in the next intake, and ovality was the defect under consideration for the remaining steps of the Six Sigma DMAIC. Thank you.
So in the analyze phase, the company first performed a failure mode and effect analysis. FMEA analysis is a proactive process that helps a company to anticipate potential problems before this occur. The advantage of such an analysis is that any company can identify potential risks and then can prioritize to tackle these risks so that they do not cause significant concerns and also do not impact other processes. An FMEA analysis consists of 5 steps. The first step is defining the scope and the topic. The second step is basically making a team. The third step is that the team that is assembled forms charts for the process. The last step is the hazard analysis to identify the potential failures. And the final step is identifying how to prevent the high risk problems from happening. Now, once this analysis is done and the table for the analysis is formed, the main parameter that we are interested from an FMEA analysis is the risk priority number, or shortly known as RPN. It is basically a numeric assessment of risk which is assigned to a particular process or a particular step in a process as part of the FMEA analysis. This number is assigned by the team that is formed during the FMEA analysis, and this is basically the quantification of the likelihood of occurrence or the severity of the impact of a particular risk. And once the risks are identified, then the company will continue to work on tackling these risks. So in our case study, the FMEA table shows that ovality dominated the defects in the producing stage, since it showed the highest risk priority number of 252, whereas other problems showed a risk priority number of around 140 to 150, which were significantly less than the problem of ovality. This helped us in identifying that ovality was the major cause. But now the next step would be identifying the causes that are causing ovality. So once ovality was established as the major risk that the company had to tackle, then the company sat down to basically point out the causes that were creating this risk. And to point this out, a cause and effect analysis was done where multiple reasons were identified which were contributing to the risk of ovality. Reasons like the chuck holding pressure inside the machines, the type of tool wares and tool holders that were used inside the machines, the physical reasons that were associated with the workers like operating fatigue, the skill of labor, reasons like hardness of workpiece inside the material category and the level of water in the coolant used inside the material category, and other reasons that originated from the domain of environment, inspection and methods. The problem here was that numerous causes were depicted depicted in this cause and effect diagram, and it was decided to consider only the major causes to pursue further implementation study. Once the identification of the above causes was done, for further consideration, the sigma level of the quality was projected in the absence of ovality that happened due to the above three causes. So the associated calculations carried out in this regard will now be presented. We have that the total number of defected stage casing units produced were 31, whereas the total number of defected stage casing units rejected due to ovality were 5. Hence, the total number of defected stage casing units which were present in the absence of ovality is basically the difference of the total number of defective stage casing units produced and the total number of defective stage casing units rejected due to ovality, which basically means that there were 26 defective stage casing units in the absence of ovality. We had that the number of opportunities were 5, which means that defects per unit would be equal to 26 by 750, as the total number of casing units produced was 750. This gives us a value of 0.034 for defects per unit. Then to find defects per opportunity, we simply divide 0.034 by 5 and we obtain 0.0069. To find the defects per opportunity per million, we take the product of the defects per opportunity with 1 million and we obtain that 6,933 defects were present in per million. And now this gives us a projected sigma value of 3.97. And hence, on overcoming ovality, the sigma level quality of producing stage casing units is expected to increase from 3.9 to 3.97.
The fourth phase in this process involves implementing and verifying the solution. So in our case study, the improvement phase involved a theoretical study on what causes ovality. So that the improvements to minimize ovality during the machining process can be made. Ovality can be defined as the degree of deviation from perfect circularity of the cross-section. Several factors can introduce ovality during machining, such as high holding pressure, tool life, depth of cut, and uneven feed. Therefore, in this phase, a two-pronged approach was taken to make improvements. Firstly, experiment was conducted to determine values of factors that give minimum ovality, and secondly, design of special devices to avoid ovality in the first place. For the experimentation part, 3 factors were included in the study, namely holding pressure, depth of cut, and tool life. Machining of the stage casing units was done with different sets of values of the factors, and afterwards ovality was measured. It was found that the minimum ovality that can be obtained is 0.1 millimeters, which occurs when holding pressure is set at 12 bars with a 2 millimeter depth of cut, irrespective of the tool wear. The operators can now utilize this information while machining stage casing units to obtain least ovality. During the study, it was also found that there was an issue with how the stage casing unit was held during the machining process. The 3-jaw chuck used to hold the casing unit from below only had a 5 mm limited contact holding length, which meant that the operators had to apply unnecessary high pressure to avoid the casing from slipping away from the chuck. This was causing uneven application of holding pressure, introducing ovality in the casing. For this reason, an improvement was made by welding an attachment to the 3 jaws of the chuck, which allow for uniform application of holding pressure, which prevents the occurrence of ovality in stage casing units to a significant degree. Furthermore, introduction of non-destructive testing (NDT) of cast units was considered before the machining process to prevent faulty castings to enter into the machining phase. But this was not implemented due to the costs associated with the acquisition of an NDT unit, since limited cost is a constraint. However, the fifth phase of the process is about maintaining the solution. The most important thing to ensure in the control phase was that the improvements suggested earlier are properly implemented and sustained. This involved keeping a check on the operators and creation of a separate inspection room where casts can be continuously inspected, and the faulty ones are kept separately in a bin in order to prevent such casts from entering the machining phase. The operators play a crucial role in this phase because it is up to them to follow the suggestions and keep different factors such as holding pressure and depth of cut at the desired values to minimize and eliminate defects. And so now we saw how using the DMAIC process, the company was able to maintain its implemented improvements.
In conclusion, we see that the pump manufacturing company was able to improve its sigma level from 3.9 to 3.97. However, there were some limitations that we identified in the study. One was that it only focused on a limited number of factors from the several that were identified, if you recall the cause and effect diagram. And secondly, the experimental results we believe were not repeated enough for validating the data that was acquired, and that makes us a little skeptic of the results. The overall study does demonstrate the power of Six Sigma as a tool for improving the processes of medium-scale businesses. However, the identified limitations do make us a little skeptic of the final results, which we believe could have been improved if they had a stronger analyze phase.